Hello everyone, in this video we're going to be going over weighted graphs. So weighted graphs are going to be the last topic for today, and in this just introduction to graphs section, and we're going to kind of wrap up with talking about weighted graphs and also why we care about graphs at all. So starting off, weighted graphs, so far you've only seen unweighted graphs. So this is a graph and it costs the same amount, going from this node to the next node and this node to this node is the same amount of effort. But we can say if these nodes represent towns on a map, and the edges are roads in between them, they might have a different distance between this node and this node. This line might not be the same as this line between these two nodes. And we don't want to do everything just to scale, so the way we represent that is what we use weighted graphs, and we have weights on each of these edges. So it maybe is 5 miles between this node and this node, but it's only 1 mile between this node and this node because of the weight on these edges. These don't have to represent distances, but it's some cost, some amount of cost that the program should be paying attention to are represented by these numbers. So a weighted graph, each edge has some number associated with it. Now, not all these numbers have to be the same. We could have everything being the same cost to go through. This is basically equivalent to an unweighted graph, but we could also have two edges with the same weight. We could have a directed, as in this case, directed graph, where it costs 1 to go from this node to this node, but going back in the opposite direction costs 5. So the weighted graphs can be combined with other types like directed graphs to create more and more complicated systems. Now, why do we care about these things? Say we're in location A and we want to get to location C. Now, there are 3 ways we could do this. We could go from A to D to E to C, and that is a path of 3 steps, right? 1, 2, 3 steps from A to C. We could also go from A to E to C, and this is a 2-step path, and so that looks faster to us, right, than our 3-step path that we did in the last pass. So path 2 is faster than path 3, and then the last path is path 3, which is A to B to F to C. And again, that's 3 steps, so that and path 1 are the same length. Neither of them is as good as path 2. So in this example for the undirected graph, path 2 wins. It's the fastest way from A to C. When we put in distances, though, or costs, weights to our graph, this may change. So for example, now when we're looking at the same 3 paths, path 1 has 2 plus 1 plus 4 to its path, so that's a path of 7, a cost of 7 there. Our previously shortest path has now a cost of 10. That 6 plus the 4 makes it a more costly path than the first path. And then our last path is 3 plus 1 plus 1, which is 5, which makes that path now the shortest way to get from A to C. And again, these types of things can represent getting electricity or water or messages or just your driving route from one place to the next. And that's the kind of thing we're going to be trying to represent in graphs, in graph theory. So there's a worksheet on weighted graphs, and that is all for graphs today. There are 2 activities for you to do. One is a video and one is a series of worksheets and that you can do with graphs, and there are fun games you can play with the graphs in those worksheets. So go do both of those things, and I hope to see you either in a Zoom meeting or in a video next week.